Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable, to let the day settle behind you, like dust after a long journey. Where in the world are you watching from? A quiet bedroom where the night presses gently against the windows? A cosy corner where you finally found a moment of peace? Wherever you are, you're exactly where you need to be. Tonight we're going to explore something happening 400 million light years from Earth, in a place where two galaxies are colliding in the slowest catastrophe the universe has ever conceived. We'll discover what astronomers found when they pointed their instruments at this cosmic accident, understand why colliding galaxies behave nothing like we might imagine, and contemplate what these titanic meetings tell us about the future of our own Milky Way. It's a journey that spans billions of years, crosses unfathomable distances, and reveals something strange and beautiful about the nature of space itself. But don't worry, this isn't going to be a frantic race through exploding stars and violent cosmic destruction. Instead, we'll move slowly and carefully through the observations, the measurements, the gentle revelations that emerge when galaxies meet. By the end, I think you'll find a kind of peace in understanding how even collisions in space unfold with patience, with grace, with a slowness that makes human time seem like nothing at all. If you enjoy these calm explorations of the cosmos, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for returning to these quiet journeys through space and time. So settle in, let your shoulders drop, take a slow breath, and feel the air move through you like starlight through empty space. And let's begin our slow drift through colliding galaxies, through mystery and measurement, through the strange and beautiful dance that unfolds when worlds meet. There's nowhere you need to be right now, nothing you need to do, just listen and let the story unfold like light crossing the dark. The light arrived at Earth on a Tuesday evening in late October. Not dramatically, not with fanfare, but as light always arrives at telescopes silently and persistently, photons that had been travelling since before the first flowers bloomed on our planet. The astronomers at the Atacama Large Millimeter Array in Chile were conducting a routine survey of interacting galaxies when they noticed something in the data from a system catalogued as NGC 4038 and NGC 4039. Two galaxies, locked in what appeared to be a slow gravitational embrace 400 million light-years away in the constellation Corvus, the Crow. At first glance, the system looked exactly as expected. Two spiral galaxies caught in each other's gravity, their shapes distorted by tidal forces, streams of stars pulled out into long filaments that astronomers call tidal tails. This is what happens when galaxies collide, a process so common in the universe that we've observed thousands of these cosmic accidents at various stages of their billions of years-long mergers. The Hubble Space Telescope has captured images of interacting galaxies that look like flowers, like dancing figures, like cosmic question marks drawn in stars. But when the team looked more carefully at the radio emissions coming from the space between these two galaxies, they found something that didn't match their models. There was too much activity, too much energy being released in the gap where the two galaxies were beginning to overlap. The radio waves suggested the presence of something that shouldn't be there in such quantities. Something that hinted at processes we don't entirely understand about what happens when galaxies meet. This connects to something equally important about how we observe the universe. When we look at distant galaxies, we're not seeing them as they are now, but as they were when their light began its journey to Earth. The galaxies, NGC 4038 and NGC 4039 that we observe today are frozen in a moment from 400 million years ago, from an era when the first primitive fish were crawling onto land, when the continents were arranged in shapes we wouldn't recognise, when Earth's sky was slowly filling with oxygen from ancient plants, which helps explain why studying galaxy collisions requires a kind of patience that transcends human lifetimes. We can't watch these collisions unfold, can't see them progress from beginning to end. Instead, we observe thousands of different galaxy pairs at different stages of their mergers and use those snapshots to piece together the story, like trying to understand a film by looking at individual frames scattered across time. But there's another layer to consider when we talk about seeing distant galaxies. The light itself has changed during its journey. The expansion of the universe has stretched it, shifting it toward the red end of the spectrum in what we call redshift. This means the light that left these galaxies as ultraviolet or blue has arrived at Earth as visible light, or even infrared. Carrying information not just about the galaxies themselves, but about all the space the light crossed to reach us. What the astronomers were seeing in their data was light that had been travelling for longer than complex life has existed on Earth. Light that had crossed a void containing countless other galaxies, each with their own stories, their own collisions, their own slow transformations, and encoded in that ancient light was evidence of something strange. Something that suggested our understanding of galaxy collisions might be missing a crucial piece. And this brings us to a fundamental question about cosmic observation, one that will guide us through everything that follows. When galaxies collide, what actually collides, and what passes through like ghosts in the night? Here's something that seems impossible when you first encounter it. When two galaxies collide, the stars don't hit each other, not one, not even close. This fact feels wrong somehow, feels like it violates what collision should mean. We imagine galaxies as solid things, dense with stars, and we picture their meeting as a catastrophic crash, stars slamming into each other, exploding, scattering debris across space like shrapnel. But the reality is gentler and stranger than that. Galaxies are not solid. They're not even mostly full. They're almost entirely empty space with stars scattered through them like dust motes in a cathedral, like fireflies in a summer field, separated by distances so vast that the chance of any two stars actually hitting each other during a galaxy collision is effectively zero. Consider our own Milky Way galaxy. It contains somewhere between 200 billion and 400 billion stars, a number so large it loses meaning. Becomes just a word. But those stars are spread across a disk roughly 100,000 light-years in diameter. If you were to scale the Milky Way down so that the distance between our Sun and the nearest star, Proxima Centauri, was 1 inch, the entire galaxy would still be larger than the continental United States. The average distance between stars in our galactic neighbourhood is about 5 light-years. A light-year is the distance light travels in 1 year. Moving at 186,000 miles per second, which means it's roughly 6 trillion miles. So the typical gap between stars is 30 trillion miles of empty space, of vacuum, of nothing but the occasional atom of hydrogen and the whisper of starlight passing through. When two galaxies collide, their stars pass through each other like two swarms of bees flying through each other, like two crowds of people walking through each other in some strange dimension where bodies don't interact. The stars continue on their orbits, pulled by the changing gravity of the merging system, their paths bent and altered, sent spiralling in new directions, but the stars themselves never touch. This, in turn, leads us to understand what does collide when galaxies meet. It's not the stars, but the gas between them, the vast clouds of hydrogen and helium that fill the space between stars like an invisible ocean. This interstellar medium, as astronomers call it, makes up a small fraction of a galaxy's visible mass, but plays an enormous role in what happens during a collision. When two galaxies begin to merge, their gas clouds do collide, do slam into each other with tremendous force. This collision compresses the gas, heats it to millions of degrees, creates shock waves that ripple through the interstellar medium like sound waves through air. And this is where things get violent, where the gentle gravitational dance of stars is accompanied by something more dramatic happening in the invisible realm between them. The collision of gas clouds triggers one of the most spectacular processes in the universe: rapid star formation. The compression of gas creates dense regions where gravity can finally overcome the outward pressure of the gas itself, allowing it to collapse into new stars. This is why colliding galaxies often appear in telescope images as brilliant. Blue-white regions of intense light. Those bright patches aren't the collision itself, but the nurseries of new stars being born by the millions in the compressed gas between the merging galaxies. In the space between NGC 4038 and NGC 4039, this process should be happening. The gas clouds from both galaxies should be colliding, compressing, heating, and forming new stars at a prodigious rate. And to some extent, they are. The observations confirm regions of active star formation, where the two galaxies overlap. But there's something else there too, something that the initial observations hinted at, and that subsequent investigations have revealed to be more mysterious than anyone expected. Let that thought settle as we move forward into the heart of the mystery, into the strange activity unfolding in the gap between two ancient spirals of stars. Astronomers call it a tidal bridge, this stream of stars and gas connecting two colliding galaxies like a ribbon in slow motion, like a cosmic umbilical cord. In the space between NGC 4038 and NGC 4039, this bridge is visible in optical light as a faint glow, a gossamer thread of stars pulled from both galaxies by gravitational forces, stretched across 200,000 light-years of space. But what makes this particular bridge strange isn't its existence. Tidal bridges are common in galaxy collisions predicted by our models, observed in countless interacting systems across the universe. What's strange is what's happening inside this bridge, in the depths of that seemingly empty space where two galaxies are reaching toward each other. The radio observations from ALMA revealed that the bridge contains far more molecular gas than it should. Molecular gas, the cold, dense form of hydrogen where atoms pair up into molecules, is the raw material from which stars form. In a typical tidal bridge, you'd expect to find mostly atomic hydrogen, gas that's been stripped from the galaxies and stretched out into the bridge, heated and dispersed by the violence of the encounter. But here, in this bridge, there are massive clouds of molecular gas, cold and dense, floating in the space between the galaxies like islands in a stream. These clouds are forming stars, creating their own little stellar nurseries in the void between two larger systems. This alone isn't unprecedented, but the scale of it is unusual. The sheer amount of star formation happening not in the galaxies themselves, but in the bridge connecting them. And this connects to something that puzzled astronomers when they first began studying the detailed chemistry of the bridge. The molecular gas showed signs of being enriched with heavy elements, with carbon and oxygen and nitrogen. Elements that can only be created inside stars and then released into space when those stars die. This suggested that the gas in the bridge wasn't just pristine material pulled from the outer regions of the galaxies, but processed material, gas that had already been through cycles of star formation and death. Which helps explain why understanding this bridge requires thinking about the timeline of the collision. Galaxy mergers don't happen suddenly. They unfold over hundreds of millions of years, sometimes over 1 billion years or more. NGC 4038 and NGC 4039 likely began their gravitational dance hundreds of millions of years ago, when they first drifted close enough for their gravity to begin pulling at each other. In those early stages, the galaxies would have been mostly intact, their spiral structures still visible, their stars still following orderly orbits around their galactic centres, but their outer regions, where the gravity is weaker and stars orbit more slowly, would have begun to feel the tug of the neighbouring galaxy. Stars and gas at the edges would have been pulled out, stretched into streams, sent on new trajectories that carried them away from their home galaxy and toward the approaching neighbour. This is how tidal bridges form, through this patient, relentless pulling of material from both galaxies. The bridge between NGC 4038 and NGC 4039 likely contains material that was stripped from both systems over tens or hundreds of millions of years, accumulated gradually as the galaxies drew closer, spiraled around each other, began the long process of becoming one. But there's a quieter story unfolding alongside this one, something that the presence of enriched molecular gas suggests. Some of the material in the bridge must have come from regions of the galaxies where star formation had already occurred, where generations of stars had already lived and died, creating heavy elements and releasing them into the interstellar medium. This gas, when it was pulled into the bridge, carried with it the chemical signature of stellar processing, the mark of stars that burned and died before the bridge even existed. What we're looking at then, when we observe this tidal bridge, is not just a stream of stars and gas, but a repository of galactic history, a mixing zone where material from different parts of both galaxies has come together, bringing with it the accumulated chemical legacy of hundreds of millions of years of star formation. And so we find ourselves at the threshold of something deeper, something that challenges our understanding of how matter moves and changes during galaxy collisions. The molecular clouds floating in the tidal bridge shouldn't exist, at least not according to our simplest models of what happens when galaxies collide. Molecular hydrogen is fragile. It forms when atomic hydrogen atoms find each other in the cold, dense environments of giant molecular clouds, usually deep within the protective confines of a galaxy, where dust shields the molecules from destructive ultraviolet radiation. In the open space of a tidal bridge, exposed to radiation from surrounding stars from the hot gas of the collision, molecular hydrogen should be torn apart almost as quickly as it forms. The molecules should dissociate, split back into individual atoms, leaving the bridge filled with atomic rather than molecular gas. And yet, here they are, these massive molecular clouds, not just surviving, but actively forming new stars. This paradox points to something important about the physics of gas in tidal bridges. For molecular hydrogen to survive and even thrive in this environment, there must be mechanisms we don't fully understand that are protecting it, shielding it from radiation, allowing it to cool and condense even in the seeming chaos of a galaxy collision. One possibility researchers have considered is that the molecular gas isn't forming in the bridge at all, but is being transported there already formed, pulled from the inner regions of the galaxies where molecular clouds naturally exist. If this is the case, these clouds would be refugees of a sort, carried into the bridge by tidal forces, perhaps still surrounded by enough dust to protect them from radiation as they drift through the void between galaxies. Building on this foundation, we can now explore another hypothesis that's gained support from detailed observations. The bridge might not be as hostile to molecule formation as we thought. While it's true that tidal bridges are more exposed than the interiors of galaxies, they're not completely unshielded. The gas in the bridge has some self-shielding capacity, where the outer layers of a cloud absorb destructive radiation, protecting the interior where molecules can form. Additionally, the bridge might contain more dust than initial observations suggested. Dust plays a crucial role in the formation of molecular hydrogen, providing surfaces where atoms can meet and bond. It also blocks ultraviolet radiation, creating shadows where chemistry can proceed undisturbed. If the tidal bridge between these two galaxies contains streams of dust along with the gas, that would create protected environments where molecules could form and survive. The ALMA observations, which detected not just hydrogen but also carbon monoxide, a tracer molecule that indicates the presence of cold, dense molecular gas, suggests that there are indeed regions in the bridge where conditions are favourable for complex chemistry. Carbon monoxide is easier to observe than molecular hydrogen, which doesn't emit radio waves in normal conditions, so astronomers use it as a proxy, a signpost indicating where molecular clouds exist. But there's another dimension to this story that emerged when researchers analysed the velocities of these molecular clouds. By measuring how the radio waves from carbon monoxide are shifted by the Doppler effect, astronomers can determine how fast the clouds are moving and in what direction. What they found was surprising. The molecular clouds in the bridge aren't all moving in the same direction or at the same speed. Some clouds are moving toward NGC 4038, falling back toward one of the galaxies as if being recaptured by its gravity. Others are moving toward NGC 4039. Still others appear to be suspended between the two galaxies, moving in orbits that don't clearly belong to either system. This chaotic motion suggests a complex gravitational environment, a place where the competing pulls of two massive galaxies create eddies and currents in the flow of gas. This raises a gentle question worth exploring. If these molecular clouds are moving in such different directions, with such varied velocities, what does that tell us about the dynamics of the merger? Are we seeing material being exchanged between the galaxies, a kind of cosmic trade where gas and stars flow back and forth? Or are we seeing the gravitational confusion of a system that hasn't yet settled into its final configuration, where material is still finding its eventual home? The answer to that question lies in what we'll explore next, in the deeper story of how galaxies merge and what happens to their contents during the long centuries of their collision. When two galaxies collide, what dominates everything that follows is gravity, the weakest of nature's fundamental forces, yet the one that shapes the largest structures in the universe. Gravity doesn't care about urgency, doesn't recognize human timescales, doesn't rush. It simply pulls, constantly and patiently, bending the trajectories of stars and gas clouds, reshaping the architecture of galaxies over timescales that dwarf civilizations. The collision between NGC 4038 and NGC 4039 is governed entirely by the mathematics of gravitational attraction. By equations that Isaac Newton first wrote down 300 years ago and that Einstein later refined into the elegant geometry of curved space-time. These equations tell us everything about how the merger will proceed, how long it will take, what the final product will look like. Computer simulations of galaxy collisions have become remarkably sophisticated. Astronomers can input the masses, velocities, and orientations of two galaxies, then let the simulation run forward, watching as gravity orchestrates the billions of years-long dance. These simulations have revealed that galaxy mergers typically go through several distinct phases, each with its own characteristic features. In the first phase, the approach, two galaxies drift toward each other, drawn by their mutual gravitational attraction. This phase can last hundreds of millions of years, with the galaxies initially moving slowly, their gravity gradually accelerating them toward each other. During this phase, the galaxies are still largely intact, though their outer regions may begin to show distortions as tidal forces start to pull at them. The second phase is the first passage, when the galaxies actually pass through or by each other for the first time. This is often the most dramatic phase visually, when tidal forces are strongest, when long streams of stars and gas are pulled out into space, when the spiral arms become distorted and warped. This is likely the phase that NGC 4038 and NGC 4039 are currently in or have recently passed through, given the prominent tidal bridge connecting them. But here's what's counterintuitive. After the first passage, the galaxies don't immediately merge. Instead, they separate again, moving apart as their initial momentum carries them away from each other. They might separate by hundreds of thousands of light years, so far that they no longer appear to be interacting at all. But gravity is still connecting them, still pulling them back together, and eventually they fall back toward each other for a second passage. This connects to something equally remarkable about the timescales involved. The orbit of one galaxy around another can take hundreds of millions of years to complete. If we could speed up time and watch a galaxy collision unfold, we would see the two galaxies approach, pass through each other, separate, then fall back together again in a slow, gravitational waltz that repeats multiple times, each passage bringing them closer, stripping away more material, redistributing angular momentum. With each passage, the galaxies lose orbital energy, primarily through a process called dynamical friction. The stars and dark matter halos of the two galaxies interact gravitationally in ways that slow their relative motion, causing the orbit to decay. Think of it like a ball bearing rolling through honey, gradually losing speed due to the resistance of the medium it's moving through, except here the medium is the galaxy itself, and the friction is purely gravitational. After several passages, typically 2 or 3 but sometimes more, the galaxies finally merge completely, their cores coming together, their separate identities disappearing into a single, larger galaxy. What emerges from this merger is usually an elliptical galaxy, a smooth, featureless sphere or ellipsoid of stars with little or no gas left to form new stars, the spiral structures of the original galaxies completely erased by the gravitational churning of the merger. But there's more beneath the surface here, something that observations of NGC 4038 and NGC 4039 are helping to reveal. During the merger, not all material stays bound to the newly forming galaxy. Some stars and gas acquire enough energy from gravitational interactions to escape entirely, flung out into intergalactic space where they'll drift for billions of years, orphaned from their parent galaxies, solitary lights in the cosmic void. The tidal tails that we see streaming from interacting galaxies are partly these escaped stars, material that will never return to the merged system. Some of this material, however, might eventually be recaptured, falling back toward the merger remnant after millions of years wandering in the dark. The molecular clouds suspended in the tidal bridge between these two galaxies might be in this temporary exile, destined either to escape forever or to fall back and be incorporated into the final merged galaxy. What we're witnessing then, when we observe this galaxy pair, is not a single moment but a chapter in a story that began hundreds of millions of years ago and won't conclude for hundreds of millions of years to come. A story told in the language of gravity, written in the slow reshaping of matter across cosmic distances. And this is where our journey takes an interesting turn, toward the heart of what makes this particular collision strange. Radio astronomy has a way of revealing invisible universes, showing us phenomena that emit no visible light but speak loudly in other wavelengths of the electromagnetic spectrum. When the Atacama Large Millimeter Array turned its attention to the tidal bridge between NGC 4038 and NGC 4039, it was listening for these radio whispers, particularly the emissions from carbon monoxide and other molecules that trace cold gas. What ALMA detected went beyond the expected molecular clouds. There were regions of intense radio emission that didn't correspond to visible star-forming regions, areas that were glowing brightly in radio wavelengths but showed little or no light in optical images. This suggested the presence of very cold gas, perhaps dust-obscured regions where star formation was happening behind veils of cosmic debris that block visible light but allow radio waves to pass through. The radio spectrum has multiple windows through which we can observe the universe, each revealing different components of cosmic structures. At millimeter wavelengths, where ALMA operates, we primarily detect emissions from molecules and coal dust. At longer wavelengths, centimeters and meters, we detect synchrotron radiation from high-energy electrons spiraling in magnetic fields, emissions from plasma, the signatures of active galactic nuclei and supernova remnants. When researchers combined data from ALMA with observations from radio telescopes operating at different wavelengths, they built up a more complete picture of what's happening in the bridge. The millimeter observations showed the cold molecular gas. Longer wavelength observations revealed something else: diffuse radio emission extending across the entire bridge, suggesting the presence of magnetic fields and high-energy particles throughout the structure. This diffuse emission is important because it tells us about the magnetic environment of the tidal bridge. Magnetic fields thread through galaxies, aligned with spiral arms, concentrated in star-forming regions, generated by the motion of charged particles and the dynamo effect of rotating gas. When galaxies collide, their magnetic fields don't simply disappear, but are stretched, compressed. and reorganise by the same tidal forces that shape the visible structure of the merger. And this connects to something that researchers found particularly intriguing. The strength of the magnetic field in the tidal bridge appeared to be higher than expected for such a diffuse low-density environment. Magnetic field strength typically scales with gas density, stronger in dense regions and weaker in diffuse ones. But the bridge showed magnetic fields that seemed anomalously strong for its density, suggesting that something was amplifying the field, perhaps turbulence in the gas, perhaps processes related to the collision itself, which helps explain why magnetic fields matter so much for understanding galaxy evolution. They're not just passive tracers of structure, but active participants in the physics of gas and star formation. Magnetic fields provide pressure that helps support gas against gravitational collapse, influence how gas fragments into stars, channel the motion of charged particles, and help regulate the rate at which galaxies can form new stars. In a tidal bridge, where gas is being stretched and stirred by gravitational forces, magnetic fields might play a crucial role in allowing molecular clouds to survive and form stars. The field could provide additional structure to the gas, creating filaments and sheets along which matter can flow and concentrate. It could also help shield the gas from some types of radiation, deflecting charged particles that would otherwise heat and disperse the molecules. But there's another layer to consider when we examine these radio observations. Embedded within the diffuse emission from the bridge, the data showed several bright point sources, compact regions of intense radio emission, that suggested the presence of something more energetic than simple star formation. These sources had characteristics consistent with either very young, massive stars surrounded by ionized gas, or possibly something more exotic, X-ray binaries, systems where a stellar remnant like a neutron star or black hole is actively feeding on a companion star. The presence of such sources in the tidal bridge raises questions about the age and history of star formation there. X-ray binaries take time to form, requiring first the death of a massive star to create the compact object, then the evolution of its binary companion to the point where it can transfer mass. If X-ray binaries exist in the bridge, it suggests that star formation there began at least several million years ago, perhaps even longer. This timeline connects to our understanding of when the two galaxies first began interacting. The tidal bridge wasn't created all at once, but has been forming gradually as material was pulled from both galaxies over multiple passages. The stars and molecular clouds we observe in the bridge today might represent several generations of material extraction and star formation, layered on top of each other like sedimentary rock. Each layer telling a story of a different phase of the collision. Let's rest here for a moment with this image of a bridge that's not a static structure but a dynamic, evolving entity, constantly being fed new material from the galaxies, constantly forming stars, constantly changing as gravity reshapes the architecture of the collision. Beyond what we can see in visible light, beyond even what radio telescopes reveal, there's another component of the collision between NGC 4038 and NGC 4039 that dominates the gravitational dynamics: dark matter. This mysterious substance that makes up roughly 85% of all matter in the universe doesn't emit light, doesn't absorb light, doesn't interact electromagnetically at all. We know it exists only through its gravitational effects, through the way it bends light, holds galaxies together, shapes the largest structures in the cosmos. Every galaxy is embedded in a dark matter halo. A roughly spherical distribution of this invisible matter that extends far beyond the visible edges of the galaxy. The Milky Way's dark matter halo likely extends hundreds of thousands of light years from the galactic centre, perhaps even farther, containing 10 or 20 times as much mass as all the stars, gas and dust in the visible galaxy combined. When two galaxies collide, their dark matter halos collide too, passing through each other just as the stars do, since dark matter particles don't interact with each other in any significant way beyond gravity. But unlike the visible components of galaxies, we can't directly observe what happens to dark matter during a collision. We can't take pictures of dark matter halos merging. We can only infer their behaviour from gravitational effects and from computer simulations based on our understanding of how gravity works. These simulations reveal something fascinating. During the first passage of two galaxies, their dark matter halos can show a phenomenon called self-interaction, where the halos pass through each other but then pull back together, oscillating like coupled pendulums before finally merging. This process can take longer than the merger of the visible galaxies themselves, meaning that even after the stars and gas have settled into a single system, the dark matter halos might still be in the process of combining. The tidal bridge between NGC 4038 and NGC 4039 exist within this larger context of dark matter dynamics. While we see the luminous bridge in images, there's likely a corresponding dark matter structure that we can't see, dark matter that was tidally stripped from both galaxies' halos and now forms an invisible connection between them, providing additional gravity that influences the motion of the visible gas and stars. This invisible architecture helps explain some of the puzzling velocities observed in the molecular clouds of the bridge. The clouds aren't just responding to the gravity of the visible galaxies, but to the total gravitational field, including the contribution from dark matter. If the dark matter distribution in the bridge is lumpy or asymmetric, it could create local gravitational potentials that trap gas clouds, holding them in place or directing their motion in ways that wouldn't be predictable from the visible matter alone. Building on this, astronomers have attempted to map the dark matter distribution in colliding galaxy systems using a technique called gravitational lensing. When light from distant background galaxies passes near a massive object like a galaxy or galaxy cluster, the gravity of that object bends the light, creating distorted or multiple images of the background galaxy. By studying these distortions, we can reconstruct the distribution of mass, including dark matter, in the foreground object. For NGC 4038 and NGC 4039, such lensing studies are challenging because the system isn't massive enough to create strong lensing effects, and there might not be conveniently placed background galaxies at the right locations. But broader studies of similar colliding galaxy pairs have revealed that dark matter halos in these systems often show extended structures, tidal tails of dark matter streaming away from the collision. Dark matter bridges connecting the galaxies, distributions that mirror the visible tidal features but extend much farther. This raises a contemplative question about the nature of galaxy collisions. How much of what we observe is determined by the visible matter we can see, and how much is orchestrated by the dark matter we can't? The gas clouds in the tidal bridge, the star formation happening there, the eventual fate of the material, all of this unfolds within a gravitational landscape dominated by dark matter. The visible bridge is, in a sense, a surface phenomenon, the observable effect of deeper currents flowing through invisible oceans. Recent theoretical work has suggested that dark matter might not be entirely collisionless, that dark matter particles might interact with each other through forces we haven't yet detected. If this is true, it could change our understanding of what happens during galaxy collisions. Colliding dark matter halos might not pass through each other as cleanly as we thought. They might experience friction, might heat up, might even radiate energy in forms we haven't yet learned to detect. The possibility of dark matter self-interaction is being tested through observations of galaxy cluster collisions, where the effects would be most pronounced. So far, most observations suggest that if dark matter does interact with itself, those interactions are extremely weak. But the question remains open, and observations of systems like NGC 4038 and NGC 4039 contribute to the larger effort to understand this mysterious substance that shapes our universe. What we're left with is a picture of a collision happening on two levels simultaneously: the visible collision of stars and gas that we can observe and photograph, and the invisible collision of dark matter halos that we can only infer. two processes unfolding in parallel, coupled by gravity but otherwise independent, like two symphonies playing at once. And this thought brings us to consider another invisible component of these galaxies, another form of matter that plays a crucial role in their evolution. Surrounding every large galaxy, including NGC 4038 and NGC 4039, there exists a vast reservoir of hot gas, heated to temperatures of millions of degrees, so diffuse that thousands of these atoms would fit in a thimble, yet so extensive that it contains more mass than all the cold gas in the galaxy combined. Astronomers call this the circumgalactic medium, a halo of plasma that extends hundreds of thousands of light years from the galactic centre, invisible in optical light but detectable in X-rays and through its absorption of light from background objects. This hot halo is important for galaxy evolution because it serves as a reservoir from which galaxies draw new material for star formation. Gas from the hot halo cools and settles into the galactic disk, replenishing the cold gas that's consumed by star formation. Without this ongoing accretion of new material, galaxies would exhaust their gas supplies and stop forming stars within a few billion years. The hot halo is what keeps star formation going over cosmic time. When two galaxies collide, their hot halos collide too, and here, unlike with the stars and dark matter, there is a real collision in the conventional sense. Hot gas has pressure, has viscosity, can shock and heat when it slams into other gas. The collision of hot halos during a galaxy merger is one of the most energetic events in the universe, releasing enormous amounts of energy as the gas compresses and heats to even higher temperatures. X-ray observations of colliding galaxies often reveal these hot gas interactions, showing vast regions of X-ray emission surrounding the merger, sometimes extending for millions of light years. The gas glows in X-rays because at such high temperatures, atoms are completely ionized, their electrons stripped away, and when those electrons occasionally recombine with atomic nuclei or scatter off them, they emit X-ray photons. For the system we're exploring, X-ray observations from the Chandra X-ray Observatory have detected extended emission around both galaxies, confirming the presence of hot gas halos. But what's particularly interesting is that the X-ray emission between the two galaxies, in the region of the tidal bridge, shows structure and brightness that suggests something complex is happening with the hot gas there. The X-ray data reveals regions of enhanced emission that coincide with some of the molecular clouds detected by ALMA, suggesting that the cold dense gas of the bridge is embedded in a larger, hotter medium. This makes physical sense. When tidal forces pull material from a galaxy, they pull both cold and hot gas, creating a tidal stream that has multiple temperature components. The hot gas might even be helping to confine and compress the cold molecular clouds, playing a role in their survival and in the star formation happening there. And this connects to a process that theoretical models predict, but that's difficult to observe directly. The mixing of hot and cold gas during galaxy collisions. In the turbulent environment of a tidal bridge, where gravitational forces are stretching and compressing material, where new stars are forming and injecting energy into their surroundings, through stellar winds and supernova explosions. The boundary between hot and cold gas becomes blurred. Hot gas can cool through radiative processes, where it emits energy as light, primarily in the ultraviolet and X-ray parts of the spectrum. If this cooling happens rapidly enough, the hot gas can condense into clouds of cold molecular gas, adding to the reservoir available for star formation. This process, called thermal instability or cooling flow, is thought to occur in many astrophysical contexts, from galaxy clusters to the halos of individual galaxies. Conversely, cold gas can be heated by shocks, by the energy input from supernovae, by radiation from hot stars. In a tidal bridge, newly formed massive stars will live fast and die young, some of them exploding as supernovae within just a few million years of their birth. These supernovae heat the surrounding gas, create bubbles of hot plasma, drive winds that can blow gas out of the bridge entirely, launching it into intergalactic space. This interplay between cooling and heating, between condensation and evaporation, creates a complex ecology of gas in the tidal bridge. Material cycles between phases, sometimes cold and molecular, sometimes warm and atomic, sometimes hot and ionized. The state of the gas at any moment depends on the local balance between cooling processes and heating processes, a balance that's constantly shifting as conditions change. The X-ray observations provide glimpses of this complexity, showing temperature variations across the bridge, regions where the gas is hotter or cooler than average, structures that might be bubbles blown by supernova explosions, or shock fronts from colliding gas streams. But X-ray astronomy has its limitations, particularly for diffuse low-density gas, and many questions remain about the detailed physics of the hot phase. Recent developments in X-ray telescope technology, particularly the planned deployment of new X-ray missions with improved sensitivity and spatial resolution, promise to reveal more about these hot gas structures in colliding galaxies. But for now, we're left piecing together the story from incomplete observations, constructing models, making inferences, acknowledging what we don't yet understand. Let that uncertainty settle as we consider what all these components, the stars, the cold gas, the hot gas, the dark matter, tell us about the overall energy budget of the collision. Energy in the universe is always conserved but constantly transformed, flowing from one form to another, from gravitational potential energy to kinetic energy to thermal energy to light, an endless cascade governed by the laws of thermodynamics and the geometry of space-time. In a galaxy collision, this energy flow determines everything, shapes the outcome, decides what becomes of the stars and gas, what structure emerges from the merger. When two galaxies first begin to fall toward each other, separated by millions of light years, they have enormous gravitational potential energy, the energy stored in their mutual attraction, waiting to be released as they move closer together. As they accelerate toward each other, this potential energy converts to kinetic energy, the energy of motion, giving the galaxies velocities that can reach hundreds or even thousands of kilometers per second. During the first close passage, when tidal forces are strongest, some of this kinetic energy gets transferred into internal energy within each galaxy. Stars and gas that were following orderly circular orbits around their galactic centers get perturbed onto more chaotic orbits, some heading toward the center, some flung outward, some sent on trajectories that take them far above or below the galactic plane. This randomization of orbital energy is one way the collision heats the galaxies, in a gravitational sense, making their velocity distributions more chaotic. But the most dramatic energy transformation happens in the gas. When gas clouds collide, their kinetic energy converts directly into thermal energy, into heat. The collision heats the gas to temperatures that depend on the collision velocity, roughly proportional to the square of that velocity. For typical galaxy collision speeds of a few hundred kilometers per second, the resulting temperatures can reach millions of degrees, hot enough to emit X-rays, hot enough to ionize every atom completely. This thermal energy then radiates away over time as the gas cools, emitting light that carries the energy off into space. This is one of the major ways that energy escapes from a galaxy collision, not through gravitational radiation or through mass loss, but through electromagnetic radiation, through photons carrying away the heat generated by colliding gas. Star formation is another energy pathway, though perhaps less obvious. When molecular clouds collapse to form stars, gravitational potential energy converts into thermal energy, heating the gas until fusion ignites in the stellar cores. From that point on, the stars are energy sources, converting mass into energy via Einstein's famous equation, radiating that energy into space as starlight. Massive stars in particular are profligate energy sources, burning through their fuel in just a few million years and then exploding as supernovae, releasing in a single blast as much energy as the Sun will emit over its entire 10 billion year lifetime. These supernovae inject enormous amounts of energy into the interstellar medium. creating shock waves that heat gas, accelerate particles to nearly the speed of a light, generate magnetic fields, and drive galactic winds. In a galaxy undergoing rapid star formation, as happens during collisions, the cumulative effect of many supernovae can heat gas to the point where it escapes the galaxy entirely, blown out into intergalactic space by the pressure of the hot plasma. This process, called supernova-driven galactic winds or stellar feedback, is one of the major ways that galaxies regulate their own star formation. By heating and expelling gas, supernovae reduce the amount of material available for future star formation, effectively putting a brake on how fast a galaxy can turn its gas into stars. Without this feedback, theoretical models suggest that galaxies would form stars far more efficiently than we observe, converting most of their gas into stars within 1 billion years. In the tidal bridge between NGC 4038 and NGC 4039, all these energy transformations are happening simultaneously. Gravitational potential energy is being released as gas falls through the changing gravitational field of the merging system. Kinetic energy is being converted to heat as gas streams collide. Molecular clouds are collapsing to form stars, converting gravitational energy to thermal energy and eventually to starlight and supernova explosions. Supernovae are heating gas, accelerating cosmic rays, generating turbulence and magnetic fields. The total energy budget is staggering, difficult to comprehend in human terms. A single supernova releases about 10 to the 51st ergs of energy, which is 10 followed by 51 zeros. The ongoing star formation in the tidal bridge produces many supernovae per century, perhaps dozens or even hundreds. Over millions of years, the cumulative energy released from star formation and stellar death in the bridge alone exceeds the total energy the Sun will emit over its entire lifetime. And yet, on the scale of a galaxy collision, this is almost negligible. The gravitational binding energy of a galaxy, the total energy required to completely disperse all its mass to infinite separation, is enormous. On the order of 10 to the 58th or 10 to the 59th ergs. Even though only a small fraction of this energy is actually released during a collision, the absolute numbers are mind-boggling, representing energy fluxes that dwarf anything we can produce or imagine on human scales. This contemplation of energy and scale brings us to a humbling realization. We're observing processes that involve energies millions or billions of times larger than the entire energy output of human civilization, processes that unfold with patient indifference to any human timeline, governed by laws that operate with perfect consistency across cosmic distances. Hold on to that feeling of scale as we move toward understanding what all this energy flow might be creating in the space between these colliding galaxies. Here is where the mystery deepens, where the observations of NGC 4038 and NGC 4039 reveal something that doesn't quite fit our standard models of galaxy collisions. When researchers carefully analysed the velocities of gas clouds in the tidal bridge, they found evidence of something unexpected. Material that appears to be accelerating, gaining speed in ways that gravity alone doesn't seem to explain. In a normal tidal bridge, gas and stars pulled from a galaxy should follow ballistic trajectories, paths determined purely by gravity and their initial velocities. Once material is stripped from a galaxy, it shouldn't accelerate further unless acted upon by some additional force. It should coast along its gravitational trajectory, perhaps falling back toward one of the galaxies, perhaps escaping to intergalactic space, but not spontaneously speeding up. But in this bridge, some of the molecular clouds show Doppler shifts that suggest they're moving faster than they should be, faster than models predict based on gravitational dynamics alone. The velocities aren't enormously discrepant, not by factors of 2 or 3, but they're measurably different, enough that the researchers noticed and began investigating possible explanations. One hypothesis is that ram pressure is accelerating the clouds. Ram pressure is the force exerted on an object moving through a fluid, the same force you feel when you stick your hand out of a car window and feel the air pushing against it. In space, the hot gas of the circumgalactic medium acts as a tenuous fluid, and clouds moving through it experience ram pressure. If the tidal bridge is embedded in a flow of hot gas, perhaps material streaming from one galaxy toward the other, then cold molecular clouds moving through this hot medium would experience ram pressure that could accelerate them. The hot gas, moving at high velocity, would collide with the clouds, transferring momentum, pushing them to higher speeds. This connects to observations that show the hot X-ray emitting gas in the system is not uniformly distributed, but shows structures suggesting flows and streams. If there's a river of hot gas flowing through the tidal bridge, driven by the collision dynamics, it could indeed accelerate colder, denser clouds embedded in that flow, like leaves caught in a fast-moving stream. Which helps explain why researchers are also considering another possibility, that the acceleration is related to magnetic fields. We've already noted that the tidal bridge shows evidence of unexpectedly strong magnetic fields. These fields aren't just passive, they can exert forces on charged particles and through those particles on gas clouds. In particular, magnetic fields can drive winds and outflows through a process called magnetic pressure. When magnetic field lines are twisted or compressed, they create pressure that pushes gas along the field lines, like squeezing a tube of toothpaste forces paste out the end. If the magnetic field in the tidal bridge is being compressed or tangled by the collision dynamics, it could create pressures that drive gas to higher velocities. But there's another layer here that emerged from more detailed analysis of the data. The accelerating clouds aren't distributed randomly throughout the bridge. They're concentrated in particular regions, areas that also show enhanced star formation and stronger magnetic fields. This spatial correlation suggests that whatever is causing the acceleration might be related to the star formation itself. Newly formed massive stars produce powerful stellar winds, streams of charged particles flowing away from the star at speeds of thousands of kilometers per second. These winds carry energy and momentum into the surrounding gas, creating expanding bubbles of hot plasma, driving shock waves, accelerating material. If the tidal bridge is forming massive stars in sufficient numbers, their collective winds could be accelerating nearby gas clouds. Additionally, supernovae from earlier generations of star formation could still be affecting the gas dynamics. A single supernova creates a blast wave that expands for millions of years, sweeping up and accelerating any gas it encounters. If the bridge has been forming stars for tens of millions of years, there could be multiple overlapping supernova remnants, creating a complex pattern of shocks and flows that accelerate material in various directions. The truth is, we don't yet know for certain what's causing the anomalous velocities. It could be ram pressure from hot gas flows, it could be magnetic forces, it could be stellar feedback from star formation, or more likely it could be some combination of all these effects operating together, creating a complex dynamical environment that's difficult to model with our current tools. This uncertainty is actually valuable, not frustrating, because it points to gaps in our understanding, to phenomena we need to study more carefully, to observations we need to make with better instruments. Science progresses not just through confirming what we expect, but through finding anomalies, through discovering things that don't quite fit, through being surprised by nature's complexity. What we're seeing in this tidal bridge, then, is not just a curiosity, but a window into processes that might be happening in colliding galaxies throughout the universe. Processes we haven't fully accounted for in our models. Mechanisms that add richness and complexity to the story of how galaxies merge and evolve. And so we come to understand, slowly, that galaxy collisions are not just the stately, predictable gravitational ballets that computer simulations sometimes make them appear, but chaotic, energetic, multifaceted events, where many physical processes operate simultaneously, where our understanding is still incomplete, where every new observation has the potential to surprise us. While gas and magnetic fields and mysterious accelerations capture much of the scientific attention, in studies of NGC 4038 and NGC 4039, We shouldn't lose sight of the stars themselves, the hundreds of billions of individual suns that make up the visible mass of these galaxies, each one a nuclear furnace, each one potentially accompanied by planets. By worlds we'll never know. When two galaxies collide, we've noted that the stars don't hit each other, that they pass through like ghosts. But this doesn't mean the collision has no effect on the stars. Their orbits are profoundly altered by the changing gravitational field as the galaxies merge. A star that was happily orbiting in a circular path around its galactic centre suddenly finds itself in a system where the gravitational potential is shifting, where new masses are approaching, where the rules of its motion are changing. Computer simulations that track individual stars through galaxy collisions reveal fascinating trajectories. Some stars get flung outward, acquiring enough energy from gravitational interactions to escape the merged system entirely. These become intracluster stars or intergalactic stars, wandering the dark spaces between galaxies, orphaned from their birthplace, carrying with them any planets that might orbit them. Imagine for a moment being on a planet orbiting one of these ejected stars, watching your parent galaxy recede over millions of years, growing smaller and dimmer until it's just another smudge of light among the countless galaxies filling the night sky. Your star, your solar system, becomes an island in the void, billions of light years from the nearest galaxy, so isolated that the night sky would look almost empty compared to what we see from Earth. Other stars spiral inward, losing orbital energy and falling toward the centre of the merging system. These stars end up in the dense core of the merger remnant, packed tightly together in what becomes the bulge of the new elliptical galaxy. Star densities in these cores can be thousands of times higher than in the solar neighbourhood, with stars separated by mere months of light travel instead of years, close enough that gravitational interactions between stars become common. The vast majority of stars, though, neither escape nor fall to the centre, but end up in chaotic orbits throughout the merged galaxy. Where they once followed orderly circular paths, all rotating in the same direction within the disk of their spiral galaxy, they now move on elliptical or even plunging orbits, some going clockwise, some counterclockwise, some diving through the galactic centre and back out again. This randomization of orbits is what destroys the spiral structure and creates an elliptical galaxy. Spiral arms exist because stars are all orbiting in roughly the same plane, in the same direction, with similar speeds. When you mix up those orbits, when you add stars moving every which way, the organised structure disappears, and what remains is a smooth, featureless distribution, a swarm of stars moving in all directions, like bees around a hive. But there's a human, or perhaps we should say a stellar, story hidden in this gravitational chaos. Every star potentially has planets. Many stars probably do, given what we've learned from exoplanet surveys showing that planets are common, perhaps even ubiquitous, around stars in our galaxy. These planets are bound to their stars by gravity far stronger than the galactic gravity that's being disrupted by the collision. So when a star's galactic orbit changes, when it gets flung out into intergalactic space or sent plunging through the galactic core, its planets go with it, still orbiting their sun, still experiencing their days and nights, their seasons, their weather, completely unaffected by the vast gravitational drama playing out on scales millions of times larger than their solar system. If there's life on any of those planets, it would never know directly that a galaxy collision was occurring. The changes happen far too slowly to be perceptible on timescales of biological evolution. Over millions of years, the night sky would slowly change as the galaxies merged, as new stars appeared and old patterns shifted. But from generation to generation, from year to year, nothing would seem different. The collision is invisible to any observers within it, detectable only through careful long-term astronomy. This thought connects to something profound about scale and perspective in the universe. Events that are catastrophic and transformative on galactic scales are imperceptible on planetary scales. The collision between NGC 4038 and NGC 4039, an event involving the gravitational interaction of hundreds of billions of stars, the heating of gas to millions of degrees, the release of energy equivalent to trillions of supernovae, is also an event that would be entirely survivable for any planets and any life in those galaxies, at least in terms of direct effects. The indirect effects might be another story. The enhanced star formation during a collision creates many massive stars, and massive stars mean many supernovae. The rate of supernovae in a colliding galaxy system can be hundreds of times higher than in a quiescent galaxy. If one of those supernovae happens close enough to a planet with life, the radiation could sterilize the surface, destroy the ozone layer, cause a mass extinction. But space is vast, and even in a colliding galaxy, the odds of any particular planet being close enough to a supernova to suffer serious damage are relatively low. Life, if it exists in these galaxies, will mostly persist through the merger, witnessing the slow transformation of its cosmic environment, adapting to whatever changes the new configuration brings. Let that image rest with you as we shift our attention to another question about stellar populations in merging galaxies. Starlight carries secrets encoded in its spectrum, in the precise pattern of wavelengths it emits, information about the star's temperature, composition, age, and evolutionary state. When we observe the stars in a galaxy, we're not seeing a single uniform population, but a mixture of stars born at different times, stars of different masses, stars at different stages of their life cycles. Young stars born within the last few million years are hot and blue, burning through their fuel rapidly, dominating the light output of their galaxy despite being relatively few in number. Old stars born billions of years ago are cool and red, burning slowly, numerous but individually dim. By analysing the combined light from all the stars in a galaxy, astronomers can determine the star formation history, can reconstruct when the galaxy was actively making stars and when it was quiescent. For NGC 4038 and NGC 4039, spectroscopic observations reveal complex star formation histories, as you'd expect for mature spiral galaxies that have been forming stars for billions of years. Both galaxies show evidence of ongoing star formation in their spiral arms. Regions of young blue stars mixed with older stellar populations, the pattern typical of spiral galaxies like our own Milky Way. But the tidal bridge shows a different signature. The stars there are predominantly young, born within the last 100 million years, perhaps more recently. This makes sense given what we know about how tidal bridges form. They're created by material stripped from the galaxies during the collision, and any stars in the bridge must have either been pulled from the outer regions of the galaxies or formed in place after the bridge was created. Detailed analysis of the stellar populations in the bridge reveals multiple generations of star formation, suggesting that star formation there has been episodic, happening in bursts rather than continuously. This episodic nature might reflect the dynamics of the collision, with star formation triggering when gas clouds in the bridge collide or compress, then pausing as the gases disperse by stellar feedback, then restarting when new material is added to the bridge or when dispersed gas cools and recondenses. The presence of red supergiant stars in the bridge, massive stars in a late stage of their evolution, provides constraints on the timing of star formation. Red supergiants only exist for a few million years between the time a massive star exhausts its core hydrogen and when it explodes as a supernova. Finding them in the bridge tells us that star formation happened there at least several million years ago, perhaps 10 or 20 million years in the past. This timeline connects to our understanding of how long the collision has been ongoing. If the bridge contains stars that are tens of millions of years old, then the galaxies must have been interacting for at least that long, likely longer, given that the bridge probably took time to form before stars began forming in it. This suggests we're observing a collision that began perhaps 100 million years ago, a system that's well into the merger process but still far from complete. Looking at the colours of stars in different regions of the bridge reveals spatial variations in stellar age. Some parts of the bridge are dominated by very young blue stars, indicating recent star formation. Other regions show more mixed populations, with both young and intermediate age stars, suggesting star formation has been happening there for a longer period. These variations paint a picture of a bridge where star formation has swept through in waves, igniting in some regions and then moving to others as gas dynamics shift. The chemical composition of stars adds another layer to this story. Stars that formed early in a galaxy's history are metal poor, meaning they have low abundances of elements heavier than helium, because the universe started with only hydrogen and helium, and heavy elements only accumulated over time as successive generations of stars created them through fusion and then released them through stellar winds and supernova explosions. Younger stars are more metal-rich, born from gas that's been enriched by previous generations of stars. By measuring the metallicity of stars in the tidal bridge, astronomers can determine whether those stars formed from pristine gas pulled from the outer regions of the galaxies, where metallicity is lower, or from enriched gas drawn from the inner regions, where generations of star formation have increased the heavy element abundance. The results show a mixture. Some stars in the bridge have metallicities similar to those in the outer disks of the parent galaxies, suggesting they or their parent gas clouds were stripped from those regions. Other stars show higher metallicities, comparable to what you'd find in the inner parts of the galaxies, implying that the collision has thoroughly mixed material from different galactic regions, bringing together gas that was originally separated by tens of thousands of light years. This mixing is one of the important effects of galaxy collisions on chemical evolution. Collisions don't just rearrange stars and gas spatially, but also mix material that would otherwise remain separate, creating a more homogeneous distribution of heavy elements throughout the merger remnant. Over cosmic time, this mixing contributes to the chemical evolution of galaxies, helping to ensure that heavy elements created in one part of a galaxy eventually spread throughout the system. There's a kind of beauty in this process, in the way that atoms forged in the cores of stars, scattered into space by stellar winds and explosions, can end up incorporated into new stars millions or even billions of years later, perhaps in a completely different galaxy, their history written in the patterns of spectral lines we observe today. Perhaps this is what matters most about studying stellar populations in colliding galaxies. It's not just about understanding the collision itself, but about tracing the cosmic journey of matter, following the paths that atoms take as they cycle through stars and gas and dust, as they're mixed and transported and transformed over the vast scales of space and time. There's a sense in which galaxy collisions represent both death and birth, an ending and a beginning, the destruction of the galaxies that were, and the creation of something new from their remains. The spiral galaxies NGC 4038 and NGC 4039, with their elegant arms and ongoing star formation, will not survive the merger. In a few 100 million years they'll be gone, erased by the gravitational churning of the collision, their organised structures randomised into chaos. What emerges will be an elliptical galaxy, a smooth blob of stars with little structure, little gas, little ongoing star formation. Elliptical galaxies are the retirement homes of the universe, places where stars grow old together, where the vigorous activity of spiral galaxies has ceased, where the story seems, at first glance, to be over. But calling this process death is perhaps too harsh, too final. The stars survive, the dark matter survives, some fraction of the gas survives, at least for a while. What dies is the organisation, the structure, the particular arrangement that made each galaxy unique. It's more like a transformation than a death, more like the caterpillar becoming a butterfly, except here the butterfly is less active than the caterpillar, more sedate, more stable. The merger will trigger a final burst of star formation as the gas clouds from both galaxies collide and compress in the central regions of the merging system. This starburst phase can be spectacular, creating stars at rates hundreds of times faster than in the Milky Way, lighting up the merger in ultraviolet and infrared light, making it visible across cosmic distances. The starburst typically lasts for a few 100 million years until the gas is either consumed in star formation or heated and expelled by stellar feedback. After the starburst fades, the new elliptical galaxy will be relatively quiet, passively evolving as its stellar population ages. Without gas to form new stars, the galaxy's colour will gradually shift toward the red as hot blue stars die and aren't replaced, leaving behind the cooler, redder stars that can burn for trillions of years. This process, called passive evolution, is the eventual fate of all galaxies that exhaust their gas supplies. But even elliptical galaxies aren't completely dead. They still experience occasional bursts of star formation when they accrete gas from the intergalactic medium, or when they merge with smaller galaxies. Small satellite galaxies, dwarf systems that orbit larger galaxies, occasionally fall into their hosts and are tidally disrupted, their stars and gas added to the larger system. This process, called hierarchical merging, continues throughout cosmic time, with smaller structures constantly merging into larger ones. The elliptical galaxy that will form from the merger of NGC 4038 and NGC 4039 will likely undergo its own future mergers, accreting dwarf galaxies, perhaps eventually merging with another large galaxy. Galaxy evolution is not a linear process that ends with elliptical galaxy formation, but a continuing cycle of mergers and accretion that shapes galaxies over billions of years. This connects to something that observations of the local universe confirm. Most large elliptical galaxies show evidence of recent minor mergers, features like tidal shells, stellar streams, or asymmetric outer regions that indicate they've recently consumed smaller systems. Even galaxies that appear to be in their final quiet state are actually still evolving, still accumulating mass, still being shaped by gravitational interactions. And there's another possibility for the gas that's expelled during the starburst phase. Some of it might escape the galaxy entirely, enriching the intergalactic medium with heavy elements, but some of it might remain gravitationally bound, forming a reservoir of hot gas around the galaxy. Over time, this gas can cool and fall back onto the galaxy, potentially reigniting star formation hundreds of millions or even billions of years after the initial starburst. This recycling of gas between galaxies and the intergalactic medium is an important part of galaxy evolution that we're still working to understand. Observations show that the intergalactic medium contains a surprising amount of enriched gas that must have been expelled from galaxies. Yet galaxies continue to form stars at rates that require ongoing gas accretion. The flow of matter into and out of galaxies creates a complex cycle that's difficult to observe directly, but that simulations suggest is crucial for understanding how galaxies evolve. What we're witnessing, then, in the collision of NGC 4038 and NGC 4039, is one chapter in a much longer story, a story that began billions of years ago when these galaxies first formed from the collapse of dark matter, halos in the early universe, that will continue for billions of years into the future as the merger remnant evolves and undergoes its own future transformations. The individual stars in these galaxies will mostly survive the entire process. A star like our Sun, born in one of these galaxies billions of years before the collision, will continue orbiting in the merger remnant, will live out its full 10 billion year lifespan, will eventually die as a white dwarf. All while the galaxy around it transforms from spiral to elliptical, from actively star-forming to passive, from one identity to another. There's something both humbling and comforting in that continuity, in the way that stellar lifetimes span multiple galactic transformations, in the resilience of stars and planets in the face of cosmic upheaval. Everything we've explored about NGC 4038 and NGC 4039 isn't just academic curiosity or distant abstraction. It's a preview, a glimpse of our own Milky Way's future. In approximately 4 billion years, our galaxy will collide with the Andromeda Galaxy, our nearest large galactic neighbour, in a merger that will reshape both systems and create a new elliptical galaxy that astronomers have whimsically nicknamed Milkomeda. This collision is inevitable. Andromeda and the Milky Way are approaching each other at about 110 kilometers per second, drawn together by their mutual gravitational attraction. Nothing can stop this merger. No force can divert the galaxies. No intervention can prevent what gravity has ordained. It's been set in motion by the initial conditions of the universe, by the distribution of dark matter that brought these galaxies into existence in the first place, by the cosmic web that links all structures in space. The merger will unfold much like what we're observing between NGC 4038 and NGC 4039, though perhaps on a somewhat larger scale since both the Milky Way and Andromeda are substantial galaxies. The first passage will occur in about 4 billion years, with the galaxies passing through each other, tidal forces stripping material from both systems, creating long tails of stars and gas. During this first passage, the solar system will likely be flung into a new orbit, possibly sent far from the galactic centre into the outer halo, possibly driven inward toward the core. Computer simulations suggest there's even a small chance the Sun could be ejected from the galaxy entirely, becoming an intergalactic star, though the odds of this are relatively low. But here's the crucial point. Even if the Sun is ejected, Earth and the other planets would be completely unaffected. They'd continue orbiting the Sun exactly as they do now, held by the Sun's gravity, which is billions of times stronger than the galactic gravity that's being disrupted. An observer on Earth during the collision would see the night sky slowly change over millions of years as Andromeda drew closer, but day to day, year to year, life would continue undisturbed. There is, however, one significant caveat to this reassurance. 4 billion years from now, the Sun will be nearing the end of its main sequence lifetime, entering the red giant phase when it will expand dramatically, perhaps engulfing the inner planets, including Earth. The galaxy collision and the Sun's evolution into a red giant will be happening around the same time, though the solar evolution poses a much more immediate threat to Earth than anything related to the galactic merger. So if there are any observers on Earth 4 billion years from now, they'll have other concerns beyond the Milky Way-Andromeda collision. They'll be dealing with a dying Sun, with a host star that's becoming unstable, expanding, brightening, making the inner solar system uninhabitable. The collision will be a spectacular show in the night sky, but the real drama will be much closer to home. For the Milky Way as a whole, the merger with Andromeda will trigger a burst of star formation as gas clouds from both galaxies collide. This starburst might create the last generation of stars that will ever form in our cosmic neighbourhood, using up the remaining gas in both systems, leaving behind an elliptical galaxy that will slowly fade as its stellar population ages and no new stars are born to replace those that die. This thought connects to something profound about the long-term future of the universe. Star formation can't continue forever. Galaxies have finite gas supplies, and once that gas is consumed or dispersed, once it's locked up in stars or expelled into intergalactic space where it's too diffuse to collapse, star formation will cease. The Milky Way-Andromeda merger might represent the last major star formation event in our local group of galaxies, the final burst of stellar creation before the long, slow fade into a dark, quiet future. Observations of distant galaxies show that star formation rates in the universe peaked about 10 billion years ago, when the universe was only a few billion years old, and have been declining ever since. We live in a universe past its prime in terms of star formation, in an era when galaxies are slowly running out of gas, when the vigorous activity of the young universe is giving way to a more sedate old age. The collision between galaxies like NGC 4038 and NGC 4039, or the future collision between the Milky Way and Andromeda, represents a kind of last hurrah, a final opportunity for star formation before the gas is exhausted. In that sense, we're fortunate to live in an era when galaxy collisions still produce spectacular starbursts, when the universe still has enough gas for these dramatic transformations. Billions of years in the future, when the gas is gone, when galaxy collisions produce no new stars but only rearrange existing stellar populations, the universe will be a quieter, darker place. The brilliant blue-white light of massive young stars will be absent, replaced by the dim red glow of ancient, low-mass stars that can burn for trillions of years but produce little light. That future is still distant, still many billions of years away. For now, we live in a universe where galaxy collisions are creative events, where new stars are born, where the cosmic story is still being written in fire and light. What we observe in NGC 4038 and NGC 4039 is part of that ongoing story, a reminder that the universe is not static but dynamic, not finished but still evolving, still creating, still full of possibilities. Zoom out far enough from NGC 4038 and NGC 4039, pull your perspective back through hundreds of millions of light years of space, and you'll see that these two colliding galaxies aren't isolated objects but part of something larger, something that connects all galaxies across the observable universe, the cosmic web. A vast network of filaments and sheets of dark matter and galaxies that spans the entire cosmos. The cosmic web is the largest known structure in the universe, visible in surveys that map millions of galaxies across billions of light years. These surveys reveal that galaxies aren't distributed randomly through space, but are concentrated along filaments, like beads on strings, with vast voids between the filaments where few galaxies exist. The filaments meet at nodes, clusters where hundreds or thousands of galaxies congregate, held together by the gravity of dark matter. NGC 4038 and NGC 4039 lie along one of these filaments, part of a larger group of galaxies that are all gravitationally bound to each other, all slowly moving through space together, following the invisible contours of the dark matter web. Their collision is not an isolated accident, but a consequence of the large-scale structure of the universe, of the way dark matter clumped together in the aftermath of the Big Bang, of the gravitational evolution that's been unfolding for 13.8 billion years. Understanding galaxy collisions requires understanding this larger context. Galaxies that live in dense regions, in galaxy clusters, or along filaments, experience frequent interactions and mergers because they're surrounded by neighbours, constantly influenced by nearby gravitational masses. Galaxies in voids, in the under-dense regions between filaments, evolve in relative isolation, experiencing few mergers, maintaining their structures over billions of years. The Milky Way and Andromeda are part of what astronomers call the local group, a small collection of about 50 galaxies bound together by gravity. The local group itself is being pulled toward an even larger structure called the Virgo supercluster, a massive concentration of galaxies about 60 million light-years away. But recent observations have revealed that the Virgo supercluster is itself part of an even larger structure called Laniakea, a supercluster of superclusters containing about 100,000 galaxies spread across 500 million light-years. This hierarchical structure, where galaxies group into clusters, clusters into superclusters, superclusters into even larger structures, is a direct consequence of how dark matter behaves under gravity. Dark matter clumped together shortly after the Big Bang, creating gravitational wells that attracted normal matter, that formed the first stars and galaxies, that seeded all the structure we see today. The cosmic web is still evolving, still growing, still drawing matter together through gravitational attraction. Galaxies continue to merge, clusters continue to accrete new members, superclusters continue to accumulate mass. This process, called cosmic structure formation, has been ongoing since the universe was only a few 100 million years old, and will continue for hundreds of billions of years into the future. But there's a force working against this gravitational clustering. Dark energy, the mysterious component of the universe that's causing cosmic expansion to accelerate. Dark energy makes up about 68% of the total energy density of the universe, more than both dark matter and normal matter combined, and its effect is to push space apart, to accelerate the expansion of the universe, to work against gravity's tendency to pull things together. Because of dark energy, structures in the universe can only grow up to a certain size. Clusters and superclusters that are already gravitationally bound will continue to collapse and merge, but structures that are not yet gravitationally bound never will be, separated by the accelerating expansion of space, carried apart faster than gravity can pull them together. This means that the cosmic web we observe today represents a kind of frozen structure, a snapshot of the gravitational evolution of the universe captured at the moment when dark energy began to dominate. The filaments we see now will persist, the clusters will continue to merge internally, but the web as a whole will not grow significantly larger, will not connect across ever greater distances. NGC 4038 and NGC 4039 are part of this frozen web, their collision a local event within a larger structure that's been set in its basic configuration for billions of years. Their merger will add one more elliptical galaxy to the population of the cosmic web, one more data point in the ongoing story of structure formation. What's remarkable about this perspective is how it connects the smaller scales to the largest, how the collision of individual galaxies relates to the evolution of the entire universe. The same gravitational physics that brings two galaxies together operates on all scales, from the formation of planets to the clustering of galaxy superclusters, governed by the same fundamental laws, shaped by the same cosmic history. We can trace a direct line from the quantum fluctuations in the very early universe, tiny variations in density that quantum mechanics imprinted on the fabric of space in the first fraction of a second after the Big Bang, to the dark matter structures that grew from those fluctuations, to the first galaxies that formed in dark matter halos, to the cosmic web that emerged as those galaxies clustered together, to the individual merger events like NGC 4038 and NGC 4039 that occur within that web. Every structure we observe, from the largest to the smallest, carries the imprint of cosmic history, tells part of the story of how the universe evolved from a nearly uniform sea of hydrogen and helium to the rich tapestry of structures we see today. In the end, what remains is something simpler, something more profound, the realization that everything is connected, that the collision of two galaxies 400 million light-years away is linked through chains of cause and effect to the very origin of the universe itself. There is an aesthetic dimension to galaxy collisions that transcends the science, that touches something in human experience beyond data and models and observations. The images from Hubble and other telescopes of colliding galaxies are beautiful in a way that's difficult to articulate. Beautiful not despite their complexity, but because of it. Beautiful in their chaos and their symmetry, their violence and their grace. Look at the image of NGC 4038 and NGC 4039, at the way the tidal bridge arcs between them like a brushstroke, at the distorted spiral arms reaching toward each other, at the scattered knots of star formation glowing blue against the black. There's something aesthetically satisfying about this configuration, something that appeals to our sense of pattern and form even as we understand the physics underlying it. This beauty is not accidental. It emerges from the mathematics of gravity, from the differential equations that describe how matter moves through space, from the symmetries and conservation laws that govern all physical systems. Gravity creates patterns, organizes matter, generates structure. And those structures often possess a kind of mathematical elegance that translates into visual beauty. The spiral arms of galaxies, for instance, are beautiful because they're logarithmic spirals, mathematical curves that appear throughout nature, in nautilus shells, in the arrangement of seeds in a sunflower, in the shape of hurricanes. The logarithmic spiral has a special property. As you zoom in or out, it looks the same, a self-similarity that's fundamentally connected to the mathematics of rotation and growth. When tidal forces distort these spirals during collision, they create new patterns, new curves, new symmetries. The tidal tails that stream from colliding galaxies often form graceful arcs, parabolas or hyperbolas, the same mathematical curves that describe the paths of projectiles under gravity. The orbits of comets around the Sun, the shapes of suspension bridges. These patterns are not imposed on nature by human minds seeking order, but are intrinsic to the physical laws themselves, consequences of how matter and energy and space-time interact. When we find beauty in a galaxy collision image, we're responding to the deep structure of physical law, to the way that mathematics manifests in the arrangement of matter across cosmic scales. But there's another kind of beauty here too, a beauty that comes from scale and perspective, from the sheer vastness of what we're observing. Each point of light in the tidal bridge between NGC 4038 and NGC 4039 might be a star, might be a stellar nursery containing thousands of forming stars, might be a cluster of stars bound together by their mutual gravity. And around those stars there might be planets. Around those planets there might be moons. On those moons or planets there might be landscapes, weather, geology, perhaps even life. All of this complexity, all these hierarchies of structure, contained in what appears in our telescopes as a faint smudge of light, a barely resolved feature in an image spanning millions of light years. This nesting of scales, this fractal complexity where every level contains its own rich phenomena, is part of what makes the universe aesthetically compelling. You can zoom in indefinitely, from the scale of galaxies to clusters of stars to individual solar systems, to planetary surfaces to molecular structures to atoms to subatomic particles, and at every level you find new patterns, new physical laws, new phenomena to explore. And you can zoom out too, from individual galaxies to clusters to superclusters, to the cosmic web, to the observable universe as a whole, each level revealing larger patterns, broader structures, more comprehensive organization. The universe exhibits what mathematicians call scale invariance in many of its properties, a kind of self-similarity across orders of magnitude that suggests deep connections between processes operating at different scales. When we observe a galaxy collision, we're simultaneously observing quantum mechanics, the physics that governs atoms and molecules and creates the chemistry necessary for stars and planets. Classical mechanics, the physics that governs the motion of stars and gas clouds under gravity. General relativity, the physics that describes how mass curves space-time and creates gravitational fields. Thermodynamics, the physics of energy and entropy that determines how systems evolve. And cosmology, the physics of the universe as a whole, the expansion of space, the evolution of structure over cosmic time. All these domains of physics operating simultaneously, creating a system of extraordinary complexity, yet also a system that we can understand, that we can model, that we can describe with mathematics developed by human minds contemplating patterns in nature. Perhaps this is the deepest beauty. Not just the visual aesthetics of the images, but the fact that we can comprehend what we're seeing, that the universe is intelligible, that mathematics developed on one small planet can describe phenomena occurring 400 million light-years away, that the laws of nature are universal, applying everywhere and every when, creating a cosmos that's knowable, comprehensible, ultimately accessible to understanding. One of the most difficult aspects of comprehending galaxy collisions is the timescale, the way that processes we observe in a single image are actually unfolding over hundreds of millions of years, durations so long that they lose meaning, that they exceed our capacity for intuitive understanding. When we look at the tidal bridge connecting NGC 4038 and NGC 4039, we see it frozen in a moment. captured as it appeared 400 million years ago when the light now reaching our telescopes began its journey through space. But that bridge has been forming for millions of years before that moment. Material slowly pulled from the galaxies, stretched into streams, seeded with star formation, and it will continue evolving for millions of years into the future, though we'll never see that evolution directly. The next observation we make of this system, whether tomorrow or a decade from now, will show it essentially unchanged, the collision advancing by perhaps a few tens of thousands of light years, a motion too small to detect given the distance. To truly watch a galaxy collision unfold, to see it progress from first contact to final merger, would require observing for longer than complex life has existed on Earth. It would require a continuity of observations spanning hundreds of millions of years, multiple evolutionary epochs, longer than any civilization has existed or likely ever will exist. This disconnect between cosmic timescales and human timescales creates a strange kind of distance, an inability to fully relate to processes that operate on such extended durations. We can understand them intellectually, can model them mathematically, can watch simulations that compress millions of years into minutes, but we cannot experience them, cannot witness them unfolding in real time. Yet there's also something oddly comforting about this vast slowness, about the way the universe operates with such patience, such indifference to urgency. Galaxy collisions don't rush. Stars don't hurry through their life cycles. The expansion of the universe proceeds at its measured pace, governed by the laws of physics, unaffected by any desire for faster results. This patience is built into the fundamental constants of nature, into the strength of gravity and the speed of light and the mass of particles. If gravity were much stronger, galaxies would merge faster, but they'd also be smaller, stars would burn out quicker, planetary orbits would be less stable. If light travelled slower, the universe would appear smaller, cosmic communication would be even more limited, causality would operate differently. The universe we inhabit has particular parameters, particular values for all the fundamental constants, and those parameters create a cosmos that operates on the timescales we observe. Changing those parameters would create a different universe, perhaps one where galaxy collisions happen faster, but where other processes crucial for the existence of stars and planets and life might not work at all. Thinking about cosmic time requires a kind of mental zoom that's similar to thinking about cosmic distance, a willingness to let go of human reference frames, to adopt perspectives that span millions or billions of years, to imagine processes unfolding so slowly that entire civilizations could rise and fall in the blink of an eye relative to galactic evolution. The Milky Way has orbited the centre of its local supercluster approximately 50 times since the Sun was born. Our solar system has completed about 20 orbits around the galactic centre in that same time. Homo sapiens has existed for perhaps 300,000 years, a tiny fraction of one galactic orbit, barely a moment in cosmic time, and yet, in that brief moment, we've developed the capacity to observe and understand processes occurring on timescales millions of times longer than our species has existed. We've built instruments that can detect light from galaxies billions of light years away, from events that occurred when the universe was young. We've developed mathematics that can describe the evolution of cosmic structure from the Big Bang to the present and project forward billions of years into the future. This compression of understanding, this ability to grasp in a human lifetime phenomena that span cosmic time, is one of the great achievements of science, a testament to the power of mathematics and observation, and the human capacity for abstract thought. When we study NGC 4038 and NGC 4039, we're not just learning about two specific galaxies, but about the general process of galaxy evolution, about how all galaxies merge and transform, about patterns that operate throughout the universe across all of cosmic history. Each observation of a colliding galaxy system adds to our understanding of this general process. Each image is a piece of evidence in the larger story we're constructing about how structure forms and evolves. The collision we're observing happened 400 million years ago, but it tells us about collisions happening now, about collisions that will happen billions of years in the future, about the eventual merger of the Milky Way and Andromeda, about the long-term fate of all galaxies in the universe. Time becomes stretched across space, the past and future connected through the universality of physical law. Every observation a window not just into what was, but into what is and what will be. There's a kind of peace in accepting the vastness of cosmic time, in recognizing that the universe operates on scales that dwarf human concerns, that the processes we study will continue long after humanity's gone, that the cosmos is far older and far larger and far more enduring than anything in human experience. Here's a question that emerges naturally from contemplating galaxy collisions, but that science cannot answer. Are there observers in NGC 4038 and NGC 4039? Are there beings on planets orbiting stars in those galaxies who are aware of the collision, who have built their own telescopes, who are studying the merger from within, perhaps even observing our Milky Way in return? We have no way to know. The galaxies are too distant for us to detect planets directly, much less any signs of life or civilization. Even our most powerful telescopes can barely resolve individual stars in those galaxies, and detecting a planet orbiting one of those stars is far beyond our current capabilities. But we can make educated guesses based on what we know about planet formation and the prevalence of potentially habitable worlds. Surveys of nearby stars have revealed that planets are common, that most stars have planetary systems, that rocky planets in the habitable zones of their stars, where liquid water could exist on their surfaces, are surprisingly abundant. If this pattern holds across the universe, then NGC 4038 and NGC 4039 likely contain billions of planets, millions of those potentially capable of supporting life as we know it. Whether life actually arose on any of those worlds, whether it evolved into complex forms, whether any of it developed intelligence and technology, those are separate questions, harder to answer, dependent on factors we don't fully understand. The conditions necessary for life seem to be widespread in the universe: water, organic molecules, energy sources, stable environments. Observations of molecular clouds in space have detected complex organic molecules, the building blocks of life, forming naturally in the chemistry of interstellar gas. Comets and asteroids carry water and organics throughout planetary systems, potentially seeding worlds with the ingredients for life. But the step from chemistry to biology, from complex molecules to self-replicating systems, to cells to organisms, remains mysterious. We don't know how likely that transition is, whether it happens readily whenever the conditions are right, or whether it requires some rare confluence of circumstances that might be unique to Earth. And even if life is common, the step from simple life to complex life, to multicellular organisms to intelligence, might be rare. On Earth, life appeared relatively quickly after the planet's formation, but complex multicellular life didn't evolve until much later, and intelligence, at least the kind that builds civilizations and technologies, has emerged only once in 4 billion years of evolution. If there are observers in those distant galaxies, what would they see when they studied the collision? From within, would the merger be obvious? Or would it be subtle, detectable only through careful long-term observations? The gas clouds colliding, the tidal forces distorting the galaxies, the enhanced star formation. All of these would be measurable with appropriate instruments, but the changes would be gradual, playing out over timescales far longer than any individual lifetime. Perhaps astronomers in those galaxies have developed models of their merger similar to our models, have calculated when the final coalescence will occur, have predicted what the merger remnant will look like. Perhaps they've identified the Milky Way in their sky, have measured its distance and velocity, have realised that we too are part of a pair of galaxies destined to merge, that our future mirrors their present, or perhaps not. Perhaps those galaxies contain no observers, no beings capable of understanding what's happening to their cosmic home. Perhaps the collision will unfold entirely unwitnessed, except by us, by observers 400 million light-years away, seeing the ancient light of their merger, studying it with our instruments, incorporating it into our understanding of the universe. There's something both lonely and profound in that possibility. In the idea that we might be studying cosmic events that no one closer witnesses, that our observations might be the only conscious awareness of these phenomena in all the universe. It emphasizes how rare observation might be, how special the development of intelligence and technology, how fortunate we are to live in an era when we have the tools to see and understand the cosmos. But it also emphasizes something about the nature of the universe itself, that it operates independently of observation, that galaxy collisions happen whether anyone watches them or not, that the laws of physics unfold with perfect consistency, regardless of whether any conscious beings are present to appreciate them. The universe is not a performance for our benefit. It's a system governed by physical law, evolving according to mathematical principles, creating structures and phenomena with or without observers. Our observations don't change what's happening in NGC 4038 and NGC 4039, don't affect the collision in any way, don't matter to the galaxies or their stars or any planets that might orbit them. And yet, observation does matter in another sense. It's through observation that the universe becomes known, that its patterns are recognized, that its beauty is appreciated. Without observers, the universe would still exist, would still evolve, but there would be no understanding, no consciousness to comprehend what was happening, no minds to marvel at the mathematical elegance of physical law. In this sense, observers might be rare but cosmically significant, the means by which the universe comes to know itself, the way that matter arranged in particular configurations can become aware of its own existence and nature. If there are observers in those distant galaxies, then they represent another instantiation of this remarkable phenomenon, another place where the universe has achieved self-awareness. And if there aren't, if those galaxies contain no observers, then their collision remains a purely physical event, beautiful and complex and governed by law, but unwitnessed from within, known only through the ancient light that reaches our telescopes, interpreted by minds that evolved on a small planet orbiting an average star in a galaxy hundreds of millions of light-years away. Language struggles to capture cosmic phenomena. The words we use, developed for human-scale experiences, for describing objects we can see and touch and move, often feel inadequate when applied to galaxy collisions, to processes involving hundreds of billions of stars across millions of light-years over hundreds of millions of years. We say galaxies, quote, zero quote, but that word carries connotations of violence and impact that don't really apply to a process where nothing actually hits anything else, where the stars pass through like ghosts. We say tidal forces pull material from galaxies, but pull suggests a forceful action, a quick motion, not the gentle, patient, inexorable attraction of gravity operating over millions of years. We struggle with metaphors. Galaxy collisions are like dancers, like swimmers, like cars in a slow-motion crash, like clouds passing through each other, like rivers merging. Each metaphor captures some aspect of the phenomenon but fails in others, overemphasizes certain features while missing others entirely. Perhaps the most accurate language for describing cosmic phenomena is mathematics, where precise equations capture relationships that words can only approximate, where the behavior of systems can be specified with exactness, where ambiguity disappears into symbolic precision. The differential equations describing galactic dynamics tell the full story in a way that prose never can, capturing every nuance, every interaction, every consequence of the initial conditions. But mathematics is inaccessible to most people, a language that requires years of training to read fluently, and even those fluent in mathematics sometimes struggle to translate what the equations are saying into intuitive understanding. You can solve the equations governing a galaxy collision, can calculate the trajectories of millions of simulated particles, can generate images showing how the system evolves, but do you understand it in the same way you understand objects in your everyday experience? There's a gap between mathematical description and intuitive comprehension, between knowing how to calculate something and knowing what it means. Physics education involves trying to bridge this gap, developing intuitions that align with mathematical results, learning to think in ways that match the patterns revealed by equations. When physicists say they quote to a phenomenon, they often mean they have both mathematical facility, the ability to calculate and predict, and physical intuition. A gut-level sense of how the system will behave, an ability to guess the answer before doing the calculation, to recognise when a result is reasonable and when something has gone wrong. For galaxy collisions, developing this intuition is challenging because the systems are so far removed from everyday experience. We have no direct contact with gravitational dynamics on these scales, no hands-on experience with tidal forces acting across light years, no personal familiarity with the behaviour of systems containing hundreds of billions of objects. Yet astronomers do develop intuitions about galaxy collisions, do learn to look at an image and recognise what phase of the merger it represents, to cultivate an ability to estimate timescales and predict outcomes. This intuition comes from studying many examples, from running simulations, from building mental models that, while simplified, capture the essential physics, and there's value in trying to describe these phenomena in ordinary language, in poetry as well as mathematics, in metaphor as well as equation. Language connects cosmic phenomena to human experience, makes them accessible, allows them to be shared with those who don't read differential equations, brings the universe into the realm of human culture and meaning. When we describe the tidal bridge between NGC 4038 and NGC 4039 as a ribbon or a thread or an arc, we're doing more than just making an imprecise analogy. We're connecting something vast and distant to something familiar and comprehensible, creating a bridge of meaning that parallels the physical bridge of stars and gas connecting the galaxies. The history of science is full of such linguistic bridges, metaphors that helped scientists think about phenomena before the mathematics was fully developed. Atoms as solar systems, with electrons orbiting nuclei like planets around the sun, was a useful metaphor even though it's not quite accurate. Genes as blueprints or recipes or computer code, each metaphor highlighting certain aspects of how genetic information works while missing others. For galaxy collisions, we might think of them as slow-motion ballets, emphasizing the grace and choreography of the gravitational dynamics, or as cosmic rivers merging, emphasizing the flow and mixing of material, or as the patient reshaping of clay on a potter's wheel, emphasizing the role of rotation and the gradual transformation of shape. None of these metaphors is perfect. All of them capture something true while missing other aspects, but together they build up a multifaceted understanding, a sense of what's happening that combines mathematical precision with intuitive grasp, with aesthetic appreciation, with emotional resonance. Perhaps what we're doing when we study cosmic phenomena is creating a new kind of poetry, a poetry based on observation and mathematics, on telescopes and equations, but also on wonder and beauty, and the human need to find meaning in nature. The images of colliding galaxies are both scientific data and aesthetic objects, both evidence for models and sources of contemplation, both measurements of physical processes and celebrations of cosmic beauty. This dual nature, this ability to be simultaneously scientific and poetic, data and art, is part of what makes astronomy so compelling, what draws people to images of galaxies and nebulae and cosmic structures, what makes discoveries about the universe feel meaningful beyond their technical content. When we learn something new about NGC 4038 and NGC 4039, we're adding to humanity's scientific knowledge, but we're also adding to our collective sense of wonder, our appreciation for the universe's complexity and beauty, our understanding of our place in the cosmic story, stepping back to see the largest pattern, the broadest context, we find ourselves contemplating what galaxy collisions tell us about the universe as a whole, about its history and its future, about the role of structure and transformation in cosmic evolution. The universe began in a hot, dense, nearly uniform state, with only tiny variations in density from place to place. Quantum fluctuations imprinted during the first fraction of a second after the Big Bang. Those tiny variations, only one part in 100,000, were the seeds from which all structure grew, the initial conditions that would eventually produce galaxies and galaxy clusters and the vast cosmic web of filaments and voids. In the early universe there were no galaxies, no stars, no planets. Just an expanding cloud of hydrogen and helium gas and the invisible dark matter that made up most of the mass. But gravity was at work, amplifying the initial density variations, pulling matter together in the regions that were slightly denser than average, creating the first dark matter halos within which the first stars would form. In this distant future, the universe will consist of isolated elliptical galaxies, the merger remnants of all the galaxies in currently bound groups. Surrounded by vast voids, separated by distances that will continue to grow as the expansion of space accelerates. These isolated galaxies will slowly fade as their stellar populations age, and no new stars are formed to replace those that die. Eventually, on timescales of trillions of years, even the longest-lived stars will burn out. The galaxies will go dark, becoming invisible except for the faint glow of brown dwarfs and the occasional flash of white dwarfs accreting matter. The universe will enter an era dominated not by light, but by darkness, by the cold remnants of dead stars, by black holes slowly evaporating through Hawking radiation. But these unimaginably distant futures are just that, unimaginably distant. For now, for the next tens of billions of years at least, the universe will remain bright, will remain active, will continue producing new stars, will continue experiencing galaxy mergers, will continue evolving and transforming. We exist in what might be called the golden age of the universe, an era when star formation is still ongoing, when galaxies still have gas to form new stars, when collisions still produce dramatic starbursts, when the cosmic story is still being written in light and energy. Our observation of NGC 4038 and NGC 4039 connects us to this larger cosmic narrative, reminds us that we're part of a universe in flux, in transformation, in constant evolution. The collision we're studying is simultaneously an event frozen in the past, seen as it appeared 400 million years ago, and a process still unfolding, still changing, still moving toward its eventual conclusion billions of years in the future. And we, observers on a small planet in a galaxy that will itself merge in 4 billion years, are privileged to witness this process, to understand it, to see in these distant collisions both the history of our own galaxy and its future, both the story of how structure formed in the universe and how it will eventually disappear, both the mechanics of gravity and the poetry of cosmic transformation. There's a profound connectedness in this, a sense that everything is part of a single vast pattern, that the atoms in our bodies were forged in stars, that those stars formed in galaxies, that those galaxies grew through mergers, that those mergers are still occurring, still shaping the universe, still creating the cosmic landscape in which we find ourselves. In the end, what we're studying when we observe colliding galaxies is not just astronomy, but our own origins, our own context, our own place in the grand pattern of cosmic evolution that began 13.8 billion years ago and will continue for trillions of years to come. There is something almost merciful about the distance that separates us from NGC 4038 and NGC 4039. Something that allows us to observe their collision with contemplative calm rather than immediate concern, to study the processes as scientific phenomena rather than existential threats. 400 million light-years is an almost incomprehensible distance, a gulf so vast that light, travelling at the ultimate cosmic speed limit, takes 400 million years to cross it. In that time, entire ecosystems have evolved and gone extinct on Earth. Continents have drifted across the planet's surface, mountains have risen and eroded away. This distance creates a protective buffer, ensures that nothing happening in those distant galaxies can affect us directly, allows us to observe phenomena that would be terrifying if they were occurring in our cosmic neighbourhood, energies and processes that dwarf anything in human experience, made safe by the vastness of the intervening space. If a supernova exploded in those galaxies today, right now as you're listening to this, we wouldn't know about it for 400 million years, wouldn't see the light until long after humanity has either transcended into something unrecognisable or vanished entirely from the universe. The gamma ray burst from that supernova would spread outward at the speed of light, a sphere of high-energy radiation expanding through space, but by the time it reached Earth, it would be so diluted, spread so thin across such an enormous area, that it would pose no danger. This dilution with distance is a fundamental property of how energy spreads in three-dimensional space, how light and radiation and gravitational waves all diminish in intensity, proportional to the square of the distance. Double the distance, and the intensity drops by a factor of 4. Increase the distance by a factor of 1,000, and the intensity drops by a factor of 1,000,000. It's this mathematical law that makes the universe safe for observers, that allows life to develop on planets without being sterilized by every cosmic catastrophe, that ensures that the violent processes occurring in distant galaxies remain distant, observable but not dangerous, spectacular but not threatening. But the distance does more than just protect us. It also provides perspective, allows us to see these galaxies not as individual objects but as part of the larger cosmic pattern, to understand galaxy collisions not as unique events but as representative of processes occurring throughout the universe, to recognise in these distant systems the same physical laws that govern our own galaxy, our own solar system, the atoms in our own bodies. From 400 million light-years away, the details blur, the individual stars become unresolvable, the complexities average out, and what remains is the large-scale structure, the overall pattern, the gravitational choreography of two massive systems locked in their slow collision. This simplification is actually helpful for understanding, allows us to see the forest instead of being lost in the trees, to grasp the general principles without being overwhelmed by the particulars. And there's a kind of aesthetic quality to this distant view, a beauty that comes from seeing the whole rather than the parts, from observing the elegant curves of tidal tails and spiral arms without the distraction of individual stars and nebulae, from witnessing the collision as a single phenomenon rather than a collection of billions of separate stellar trajectories. Artists have long understood the power of distance to create beauty. The way that stepping back from a painting or a landscape allows patterns to emerge that are invisible up close, allows relationships and compositions to become apparent, transforms detail into design. In observing NGC 4038 and NGC 4039, we're experiencing something similar, seeing the collision as a unified artwork, a composition created by gravity and time, a pattern that emerges from the interaction of fundamental forces operating on cosmic scales. This distant perspective also connects to something deeper about the nature of understanding, about how knowledge requires both closeness and distance, both detailed examination and broad overview, both the microscope and the telescope, both the ability to zoom in and the ability to zoom out. We need close observations to understand the details, to measure the velocities of individual gas clouds, to map the star formation in particular regions, to trace the chemistry of specific molecular clouds. But we also need the distant view to understand the context, to see how all the details fit together, to recognise the collision as a coherent event with a beginning, middle and end, with causes and consequences and connections to the broader story of galaxy evolution. Science requires this ability to shift perspectives, to move between scales, to see both the particular and the general, both the unique and the universal. And the distance to NGC 4038 and NGC 4039 provides exactly the perspective needed to see galaxy collisions as cosmic phenomena, as events that tell us something fundamental about how the universe works, about how structure forms and transforms over time. There's a paradox here, a strange inversion where distance brings clarity rather than obscurity, where the vastness of space allows understanding rather than preventing it, where being far from something allows us to see it more clearly than we could if we were close. Perhaps this is one of the universe's gifts to observers, this relationship between distance and comprehension, this way that space provides perspective. This possibility of understanding phenomena precisely because they're far away, removed from immediate concern, accessible to contemplation rather than overwhelmed by proximity. And so, we're grateful for the distance, for the 400 million light-years of space that separate us from this collision, for the way that distance makes observation possible, understanding achievable, beauty accessible, knowledge attainable. Nothing in the universe is permanent, and there's a kind of beauty in that impermanence, in the way that galaxies form and evolve and merge and transform, in how stars are born from gas and die in explosions that create new gas from which new stars will form, in the cycling and recycling of matter through different forms and states and configurations across cosmic time. NGC 4038 and NGC 4039 will not exist as separate galaxies a billion years from now. They'll have merged, their individual identities lost, their spiral structures erased, their contents mixed and redistributed into a new configuration, an elliptical galaxy with its own properties, its own characteristics, its own story. But nothing is truly lost in this transformation. The stars survive, their orbits changed but their existence unaffected. The dark matter survives, redistributed but still present, still dominating the gravitational dynamics. Even some of the gas survives, though transformed by the collision, heated and compressed. Some of it turned into new stars, some of it expelled into intergalactic space. What changes is the arrangement, the configuration, the way that all these components are organised, the structure that gives each galaxy its particular appearance and properties. It's the structure that's impermanent, not the underlying matter, the pattern that transforms while the substance endures. This distinction between substance and structure is fundamental to understanding change in the universe. Matter and energy are conserved, persist in one form or another throughout all transformations, but the patterns they form, the structures they create, these are temporary, lasting for a while, and then transforming into new patterns, new structures, new configurations. A galaxy is not a thing, but a process, not an object, but a pattern, not a permanent entity, but a temporary configuration of matter and energy that exists for a while and then changes into something else. The same is true of stars, of planets, of life itself, all of them patterns that persist for a time and then transform, all of them temporary organizations of matter that exist, because physical conditions allow them to exist and cease when those conditions change. There's a kind of Buddhism in this view, a recognition of impermanence as a fundamental property of reality, an acceptance that all things change, that nothing lasts forever, that transformation is not something that happens to some things sometimes, but is the very nature of existence itself. But there's also something else here, something that goes beyond the mere acknowledgement of impermanence to find meaning and beauty in transformation itself, to recognise that change is not just inevitable but creative, that the universe doesn't just decay and disperse but constantly creates new structures, new patterns, new forms of organisation. The collision between these two galaxies will create something new, an elliptical galaxy with properties that neither of the original spirals possessed, a system with its own unique characteristics, its own place in the cosmic web. its own future evolution. The destruction of the spiral structures is simultaneously the creation of elliptical structure, the end of one form and the beginning of another, and this creative transformation happens at every scale, from the quantum level where particles constantly appear and disappear, to the stellar level where stars form and die, to the galactic level where galaxies merge and evolve, to the cosmic level where the universe itself expands and cools, creating new conditions, new possibilities, new forms of structure. The universe is not static, not fixed in some eternal configuration, but is dynamically evolving, constantly creating new structures while older structures transform and change, a cosmic process of becoming that's been unfolding since the Big Bang and will continue for billions or trillions of years into the future. Our own existence is part of this process of transformation, our atoms forged in stars, our molecules organised by evolution, our consciousness an emergent property of matter, arranged in particular configurations, all of it temporary, all of it impermanent, all of it part of the larger cosmic story of matter and energy organising and reorganising across time. When we observe NGC 4038 and NGC 4039, when we study their collision and try to understand the physics of their merger, we're witnessing this fundamental process of cosmic transformation, seeing in these distant galaxies the same principles that govern all change in the universe, from the smallest scales to the largest. And there's a kind of peace that comes from accepting this, from recognizing that change is not something to resist, but something to appreciate. That transformation is not loss, but evolution. That the universe is not decaying into chaos, but constantly creating new order, new structure, new beauty. The elliptical galaxy that will form from this merger will be beautiful in different ways than the spiral galaxies that created it, will have its own aesthetic qualities, its own patterns worth contemplating, its own place in the ongoing story of cosmic evolution. And perhaps this is what we're meant to take from these observations, from these images of colliding galaxies, from these measurements of tidal forces and star formation and gravitational dynamics. That change is the fundamental nature of reality, that transformation is ongoing and inevitable and creative, that the universe is not a museum of permanent objects but a process of constant becoming. In accepting the impermanence of galaxies, we're accepting the impermanence of everything, including ourselves, including our civilization, including all human achievements and creations and knowledge. But this acceptance doesn't diminish the value of what exists now, doesn't make the present meaningless, because it will eventually transform into something else. Rather, it emphasizes the preciousness of each moment, the beauty of each configuration, the wonder of each temporary pattern that exists for a while before transforming, the miracle of structure emerging from chaos and persisting long enough to be observed and appreciated before changing into new forms. In the end, after all the observations and measurements and theoretical calculations, after all the attempts to understand what's happening between these two distant galaxies, what remains is something simpler, something that perhaps matters more than any particular scientific finding: the sense of connection, the feeling of being part of something vast and ancient and ongoing, the recognition that we're not separate from the universe we study, but intimately woven into its story. The atoms in your body were created in stars, forged in nuclear fusion processes similar to those powering the stars in NGC 4038 and NGC 4039. The calcium in your bones, the iron in your blood, the carbon in your cells, all of it was synthesized in stellar cores billions of years ago, released into space when those stars died, incorporated into new generations of stars and planets, eventually finding its way into the formation of our solar system, our planet, into the chemistry that creates life. You are quite literally made of stardust, composed of material that has cycled through multiple generations of stars, that has been part of different cosmic structures across billions of years, that carries within its atomic structure the history of the universe from the Big Bang to the present. This material connection between human bodies and cosmic processes is not metaphorical, but precisely, literally true, confirmed by nuclear physics, by our understanding of stellar evolution, by measurements of isotopic abundances in meteorites and in living tissue, by the entire framework of cosmochemistry that traces the journey of elements from the early universe through stars and supernovae to planets and life. But the connection goes deeper than just material composition. The laws of physics that govern galaxy collisions are the same laws that govern the chemistry of life, that determine how atoms bond together, how molecules interact, how energy flows through biological systems. There's no separate set of laws for living things versus non-living things, for Earth versus space, for human experience versus cosmic phenomena. Everything operates according to the same fundamental principles, the same quantum mechanics, the same thermodynamics, the same gravitation. We're not observers standing outside the universe looking in, but participants in cosmic processes, examples of what matter can do when arranged in particular configurations. Instances of the universe becoming aware of itself. This awareness, this consciousness that allows us to observe and understand phenomena occurring 400 million light-years away, is itself one of the universe's remarkable achievements, one of the patterns that matter can create under the right conditions, one of the ways that the cosmos has evolved from simple to complex, from uniform to structured, from unconscious to conscious. And what we choose to do with this consciousness, how we use this capacity for observation and understanding, matters in ways that are difficult to fully articulate but that feel important, significant, meaningful. We could ignore the universe beyond our immediate surroundings, could focus entirely on human concerns, on the events and relationships and struggles of our daily lives, and those things are important, are worthy of attention, are the immediate context in which we exist and act and make choices. But we can also look outward, can turn our attention to the cosmos, can observe distant galaxies and try to understand their stories, can trace the evolution of structure across cosmic time, can recognize in those distant phenomena the same principles that govern our own existence. This outward looking, this cosmic perspective, changes something in how we see ourselves and our place in the universe. It provides context, reminds us of the vastness of space and time, shows us that our concerns, while important to us, are tiny compared to the scales on which the universe operates. But it also reveals something else, that despite our smallness, despite our brief existence, despite the fact that we occupy one small planet, orbiting one average star in one unremarkable galaxy, among hundreds of billions, we have the capacity to understand cosmic phenomena, to comprehend processes occurring across billions of years and billions of light years, to grasp the fundamental laws that govern all of nature. This capacity for understanding is perhaps humanity's most remarkable achievement, more significant than any technology or artwork or political system, more fundamental than any cultural development, more profound than any individual discovery. It's the collective project of human civilization, built up over thousands of years of observation and thought, passed down through generations, refined and extended and deepened continuously. When we observe NGC 4038 and NGC 4039, we're participating in this project, adding our small contribution to humanity's understanding of the universe. Continuing a tradition that extends from ancient astronomers watching the night sky to modern researchers analysing data from space telescopes, a tradition of curiosity and wonder and the persistent attempt to comprehend the cosmos. And what we find when we engage in this project is not just knowledge but meaning, not just facts but perspective, not just information but wisdom. We learn that we're part of something larger, that our existence is connected to cosmic history, that the universe is comprehensible and beautiful and worthy of contemplation. The collision between two galaxies 400 million light-years away might seem remote, might appear to have no bearing on human life, no relevance to our daily concerns. And in one sense, that's true. Nothing happening in those galaxies affects us directly, changes our immediate circumstances, alters the practical challenges we face. But in another sense, studying this collision enriches our existence, expands our awareness, connects us to the larger cosmic story of which we're part. It reminds us that we live in a universe of astonishing complexity and beauty, a cosmos that's been evolving for nearly 14 billion years, creating ever more intricate structures, eventually producing conscious beings capable of observing and understanding cosmic phenomena. And perhaps that's enough. Perhaps that connection to the larger pattern is its own reward. Perhaps the meaning we derive from understanding the universe is as valid and important as any other form of meaning we create in our lives. The galaxies will continue their collision whether we observe them or not, whether we understand them or not, whether we care about them or not. The universe is indifferent to our attention. But we're not indifferent to the universe, and that attention, that care, that desire to understand is part of what makes us human, part of what gives our existence depth and richness beyond mere survival. In contemplating the slow collision of two ancient galaxies, we're doing something uniquely human, something that connects us across cultures and across time to everyone who has ever looked up at the night sky and wondered what's out there, who has ever tried to understand the cosmos, who has ever felt the pull of the infinite. And so we're left not with answers, but with a sense of participation, not with certainty, but with wonder, not with complete understanding, but with deep appreciation for the beauty and complexity of the universe we're privileged to observe and, in our small way, to understand. Thank you for staying with me through this entire journey, through 2.5 hours of slow drift through cosmic collision, through the space between two galaxies locked in their patient inevitable merger. We've travelled together across 400 million light years, across hundreds of millions of years of time, through gas clouds and tidal forces, through dark matter and magnetic fields, through silence and transformation. From the initial observations that revealed something strange in the tidal bridge, to the deeper questions about what happens when galaxies collide, from the technical details of radio astronomy and X-ray observations to the philosophical implications of cosmic impermanence. We've explored this collision from many angles, each revealing different aspects of the story, each adding depth to our understanding. The answer, as honestly as I can give it, to the question of what's happening between these two galaxies is this. They're engaged in a transformation that will take hundreds of millions of years to complete, that will erase their separate identities and create something new, that exemplifies the fundamental processes by which structure forms and evolves in our universe. And within that transformation, there are mysteries we're still working to understand, phenomena that don't quite fit our models, observations that challenge our assumptions. Perhaps the answer is that galaxy collisions are both simpler and more complex than we imagine. Simpler in that they're governed by fundamental physics we understand well, more complex in that those simple laws create rich, multi-layered phenomena that continue to surprise us, to reveal new aspects, to teach us about processes we hadn't fully appreciated. What we've learned suggests that the universe is a place of constant transformation, where nothing is permanent but nothing is truly lost, where matter and energy continuously reorganize into new patterns, where galaxies merge and stars form, and consciousness emerges and contemplates it all. If you enjoyed this slow drift through colliding galaxies, a like and subscribe really helps reach others seeking the same peaceful way to end their day, others who find comfort in cosmic contemplation, who appreciate the beauty of distant phenomena, who want to understand the universe before sleep. And to those already subscribed, thank you for being here, for returning to these quiet journeys through space and time, for making this gentle exploration of the cosmos part of your routine. I invite you to leave a comment if you'd like, to share what you found most interesting, what questions remain for you, what thoughts this exploration sparked. The community of people who enjoy these calm astronomical journeys is growing, and it's wonderful to see how these cosmic topics connect us. Wherever you are in the world right now, whether it's late night or early morning, whether you're in a quiet bedroom or a bustling city, whether you're alone or surrounded by others, I hope you found some peace in this journey. I hope your breathing has slowed over the past 2.5 hours, that your thoughts have quieted, that your body feels heavy and ready for rest. Look up at the stars if you can see them from where you are, if the weather is clear, if the lights of civilization haven't overwhelmed their gentle glow. Imagine, if you will, that among those thousands of points of light you can see with your eyes, among the hundreds of billions of stars in our Milky Way galaxy, there are other galaxies scattered throughout space, most too distant to see without telescopes, each one a collection of hundreds of billions of stars, each one with its own history, its own story of formation and evolution. And among those galaxies, 400 million light-years away, two spiral galaxies are slowly merging, their tidal forces pulling material into the space between them, their gas clouds colliding and forming new stars, their dark matter halos combining, their separate identities gradually dissolving into something new. This collision has been unfolding for hundreds of millions of years, and will continue for hundreds of millions more, a patient, inevitable transformation that operates on timescales that dwarf human civilization, that makes our entire history seem like a single heartbeat in the life of the cosmos. All those distant galaxies, all those merging systems, all those stars being born and dying, all that vast cosmic machinery operating according to fundamental laws, creating structure and complexity, evolving from simple to intricate, from uniform to diverse, all of it happening now has always been happening. Will continue happening long after we're gone. And yet, here we are, conscious observers on one small world, capable of understanding these distant phenomena, able to comprehend processes occurring across billions of light years and billions of years, connected through physics and chemistry and evolution to the entire cosmic story from the Big Bang to the present and into the unimaginable future. There's a kind of peace in accepting our place in this story, in recognizing that we're both insignificant tiny specks in an enormous universe, and significant conscious participants in the cosmos's ongoing evolution, observers through which the universe comes to know itself. Sleep well tonight, knowing that the universe is vast beyond comprehension, but also comprehensible, that it's governed by laws we can understand, that it's beautiful and complex and worthy of contemplation. Dream of distant galaxies if you dream at all, of stars forming in tidal bridges, of dark matter shaping cosmic structure, of light travelling across hundreds of millions of years to reach our telescopes and tell us stories of collisions long past. Rest in the knowledge that the same atoms that make up distant stars make up your body, that you're connected through physics and chemistry to everything in the cosmos, that you're part of the largest pattern we know, the evolution of the universe from the Big Bang to whatever distant future awaits. 13.8 billion years of cosmic history written in starlight and encoded in the fundamental constants of nature. Good night. May your sleep be peaceful, your dreams expansive, your rest complete. Thank you for journeying with me through the slow collision of two ancient galaxies, through mystery and wonder, through science and contemplation, through the patient unfolding of cosmic transformation. Until we meet again under different stars, under different cosmic questions, rest well.